Oh, hey there! My name's Kyle Wagner, and I'm part of Team 16. One team, one dream.
Woo! My name is Greg Harold, and I'm part of Team 16 as well. We're working on the precision targeting system for a miniature UAV. Hey, you seen Alex?
No, where could he be?
What's up, guys?
Oh, what's
hey.
going on?
I'm Alex Bang. I'm the last member of Team 16. One team, one dream. Today we're here to talk to you about our project. We're first going to talk about the different requirements that we have. Then we're going to go into the technology that we're using. Then after that, we'll show you our block diagram. Lastly, we'll talk a little bit about the challenges we are facing. To kick things off, we have Kyle talking about our project overview.
The purpose of this project is to create a targeting system for a miniature UAV. We will be working in parallel with engineers from Voxel, Inc. for this project. Voxel is hoping to start using UAVs for agricultural use on large farms. Our goal is to be able to target a laser pointer within a square meter of a predetermined target. But before you can accurately target an object, you need an accurate navigation system to know your own position. Currently, the only navigation systems that are accurate enough are far too heavy for the UAV. Because of this, we need to create a system that is both lightweight and very accurate, while also being as cost-effective as possible. Our plan is to use a single GPS chip from Hemisphere GPS that is able to calculate its location quickly and very accurately. Our system is being built for use on the miniature UAVs such as the Raven from Aero Environment.
Now that Kyle has finished discussing a project overview for this assignment, I'd like to discuss some of the customer requirements that Voxel has asked that we reach in this project. First, the navigation system needs to work with the existing UAV navigation system. This will most likely be done by completely overlapping their system with our navigation system, which will be much more accurate. Next, we need to be able to point a gimbaled laser sensor within a 1 meter accuracy at a target on the ground. Next, we need to have the total weight of the system be less than half a kilogram. This is especially important because the UAV itself will only be weighing a little over 2 kilograms. The following are some engineering requirements that we feel are necessary to reach the goal for this project. First, the UAV must be able to point itself in the direction of the target within 30 seconds of launch. This means that once the UAV is launched, regardless of direction, it will be on course within 30 seconds. Next, the UAV must be able to go to at least 5 pre-programmed targets within a 1,000 square meter area, all in one launch. And finally, the UAV must be operating at a height of 25 to 35 feet. This is important because the ultrasonic rangefinder that we're using to determine our height is only accurate within those constraints, and that's a very necessary part of our navigation system. The UAV targeting system needs to be very easy to use. We don't expect our customers to have a strong technical background, and so we're striving for 4 out of 5 people being able to learn the target coordinating system within 30 minutes of training. Next, the plane needs to be able to land within a pre-programmed GPS destination with an accuracy of 10 square meters. This will be achieved by a stall and nearly crash landing, which leads us to our next and very important engineering requirement, that the UAV navigation components need to be quick release. This will be because the crash landing often will break off components of the UAV that still need to be ready for use during the next launch.
Now that Greg has talked about some of the engineering requirements, I'm going to talk about the technology that we will use to implement these requirements. First off, we will be using an ultrasonic rangefinder. Secondly, a gimbaled sensor. And thirdly, a GPS chip with RTK, which stands for real-time kinematics. The ultrasonic rangefinder is used to find the distance from the ground to the UAV. The reason we're using this instead of the GPS is that there is quite a large error associated in this measurement when doing the GPS. The reason for this is because GPS uses triangulation to calculate a horizontal coordinate. The GPS, when it's trying to find the vertical coordinate, it only can bounce waves off of it and trying to calculate how long it takes for those waves to come back. There's a lot of error in this because the wave has to travel all the way through the atmosphere. Next, I'm going to talk about the gimbaled sensor. The gimbaled sensor is what will have our laser pointer on it. The reason we're using a gimbaled sensor is that it can turn on 2 axes. By being able to turn on 2 axes, we will be able to maximize the time that we can point our laser at our target. Lastly, I will be talking about the GPS with real-time kinematics. So most GPSs have a fairly large accuracy, at least larger than what our requirements are. For this, the RTK, what it does is it takes a base station that has a known position of coordinates. It is able to read what the GPS is giving it and find the air since it knows its own location. With this air, it uses radio waves to send the information out to other RTK GPS chips. In this picture, this is our base station, while the man represents what our UAV will be. When a GPS measurement comes down, this base station is able to send the air differential out to our UAV. By doing this, the UAV is able to know its own position to within a very accurate range.
Alex just explained the technology being used in our system, and now we will see how it is all brought together in our block diagrams. We will look at the GPS chip. The signals coming into this chip are the signal in, power, and the air calculation. The signal in is a dual channel signal coming from the multiple satellites to give the chip its coordinates. The chip we will be using processes this information at up to 10 Hz. Next, the power in for this GPS chip is 3.3 volts plus or minus 5%. This power will be supplied from the UAV's own power source. The air calculation signal is a radio wave that comes from the base station that can be placed within 15 kilometers of a targeted area. The signal coming out of the GPS chip is in a binary format that is able to integrate with the Atmega microprocessor. Next, we will look at the base station. The base station acts very similar to the GPS chip that is on the UAV. The base station is required to stay stationary for a fairly long period of time, multiple hours to days. By doing this, the GPS chip is able to find its position to within a few centimeters. When the UAV is then in use, the base station will be able to read the current GPS position being sent. With the base station knowing its own location very well, is able to send, via radio waves, a correctional factor to the GPS on the UAV. The GPS on the UAV can then use this correctional factor to be accurate of its own position to within less than half a meter.
The Atmega 128 is a CMOS 8-bit microcontroller that can execute powerful instructions in a single clock cycle and also be optimized for power consumption and processing speed. This is especially important for this project as the UAV will need to know its location in real time, all while running on limited battery power. The Atmega 128 will take in binary GPS data and an analog signal from the ultrasonic rangefinder. Using this data, an accurate coordinate in 3 space can be determined for the UAV. These coordinates will be compared against the coordinates of the target location input by the user. A program written in C will perform trigonometric calculations on these 2 coordinates to determine the distance and angle from the UAV to the target. The Atmega 128 will need to interface with the gimbaled sensor on the UAV, but at this time the manufacturer is withholding this information. Finally, the Atmega 128 will require a supply voltage between 4.5 and 5.5 volts.
There are many unique challenges that we are faced with this project. The biggest and main one is the GPS. There becomes a fine line when you're looking at the accuracy versus the weight of the GPS. You can have a very accurate system, but it's going to weigh a lot. For our design, we need a very accurate system that also weighs a very minimal amount. This is something that people have been trying to look for a pretty long time, and a lot of money has been spent into it. So for us to find something that can work is pretty challenging. The next challenge that we come across is integrating the system. The final goal of this is to work with the Raven from AeroVironment. However, the Raven's a very expensive model, and we most likely will never be able to get our hands on it. Because of this, we probably will have to work with some cheaper companies and cheaper models, but at the same time, have it so our equipment can be integrated into the Raven eventually. Lastly, we have to look into the landing. When the Raven lands, it completely falls apart. Because of this, not only do all of our components have to be sturdy to withstand this force when it lands, but they also need to break apart so none of the wires can break. All 3 of these challenges are very unique to our project and are going to be difficult for us to conquer.
With the challenges set before us by our company Voxtel, we now have a system and design in place ready to solve these problems. Using the single GPS unit with real-time kinematics error correction and the ultrasonic rangefinder, we can successfully locate the UAV and its relationship to the target. Using this and trigonomic identities, we can pinpoint the location and aim the gimbaled sensor with a laser pointer at the target. This will give us an accuracy of less than 1 meter, and also the whole weight of the system will be less than 1/2 of a kilogram. Looking forward, we have established the following timeline to complete this project. By the end of this term, we will have selected all of our components and placed orders, and will be receiving them sometime during winter break. At this time, we will begin testing the preliminary block diagrams and work towards finalizing a prototype. By spring term, we will be finishing up any last errors or corrections to make the project better, and we'll be ready for the expo. Thank you for listening to our video, and we'll see you there.